Hello and welcome to the FlowCAD webinar, Early Analysis and Verification of Thermal Effects in PCB Design. My name is Petra. Today I'm supporting my colleagues Dirk and Bernd, who will show you what is important in first-time right design and how suitable simulation tools can be used in a targeted manner. If you have ever had contact with our support or attended a training, you probably already know our experts. A few words about them. Dirk studied electrical engineering with a focus on communications engineering and has in-depth knowledge of various software products from the EDA environment that covers signal and power integrity as well as thermal-aware electronics applications. He will introduce you the electro-thermal co-simulation using a common design example. Thermal effects on the PCB as well as the thermal behavior of components will be analyzed and evaluated. Bernd studied electrical engineering with a focus on VLSI design methodology and has extensive knowledge of the EDA environment, from chip design to the printed circuit board and the automation of data exchange between different tools. Using a typical circuit example, he will show you how piece-by-smoke analysis recognizes critical components and what measures the developer should derive from this in order to be able to operate the components safely in the circuit. That's all for the moment. Dirk, let's get started.
Thanks, Petra, for the nice introduction. I would also like to welcome you to this webinar. So, to overcome electro-thermal challenges in PCB design, tools are needed that allows the PCB designer to perform studies and analysis in different design cycles. So mainly the question is, why is thermal simulation so important? Of course, here the miniaturization of electronic assemblies and components has to be mentioned. At the same time, we have to keep an eye on energy consumption with ever lower voltages and increasing currents. Both of these factors go hand in hand with increasing power loss, which generates unwanted heat. But which key factors can already be taken into account here in this early design cycle? Here's a few typical examples. The environmental conditions like ambient temperature, any kind of airflow, or if there are any additional heat sources nearby the components. And we also have to consider the housing effects. It's important to know if we have a closed enclosure or if there are any airflow holes, or even if active cooling is implemented. Yeah, and finally, we also have to check whether the selected components are suitable for the desired application at all. And so that means that all requirements will be met. So the cheapest component is not always the best choice at system level. It may be that additional cooling concepts such as heat sinks or additional active cooling are required. So in this case, a useful compromise between the costs and benefits must be taken into account. So now let's have a look here at the first beginning phases. So most likely, the following questions arise. What tools can I use to achieve this goal? The more you take into account right at the beginning, the higher the probability that there will be no nasty surprise in the prototype phase. In the first step, you will certainly pay attention to the manufacturer-specific data sheets and design guides. But in many cases, you will deviate from the rather ideal boundary conditions and have to adapt the specified rules to your specific boundary conditions. So with the so-called piece-by-smoke analysis, you can carry out the targeted thermal stress tests when entering the circuit diagram. That gives you an indication of which components may have to be operated outside the specification or even be destroyed. So my colleague Bernd will show you in more details about this in a moment. In the next step, we assume that you have selected your components and start with the layout placement. An optimal design of the copper surface and copper planes and conductors even taking thermal effects into account. So it's certainly no longer possible to do this without the help, without using some tools, and you cannot follow only some of rules. So in this section, I will show you some approaches that can be successfully support you in your design process. So finally, 3D FEM or CFD analysis methods can be used, which you can then take a view and analyze your design at system level. So we will not go into these methods in more detail because this would be beyond the scope of our webinar. So Bernd, now we come back to the piece by smoke analysis, and I would like to hand over to you.
Okay, thanks, Dirk. Hello, also from my side. My name is Bernd Krippner, and I will show you now in the next minutes how piece by smoke helps you to optimize the component selection and enhances the PCB reliability. But before I will do that, I will just give you a brief overview of the PSpice analysis platform. Well, PSpice is not just a single point tool, not just a circuit simulator, but it's integrated in the whole design flow. So there's a tight link between the schematic authoring tool, this is Capture, and PSpice, of course. And there's also the link between the Capture and the PCB editor. This means you're creating your circuit in the same tool for the simulation as for the PCB netlist. You do not have to leave the tool. You do not have to extra draw the circuit again to do a simulation with other tools. Bring the information back into the system, and this is an error-prone way. This flow is avoiding all that problems. PSpice has also some advanced simulation capabilities. I will just mention here, for example, the tool that is called Optimizer. The Optimizer will help you to optimize circuits for their requirements. It can optimize models for the simulation, and you can optimize your whole circuits for cost and productivity. I would also like to mention the advanced Monte Carlo simulation, for example, which will give you direct access to the yield results of your circuit, so you can directly read under the circumstances what the yield of the current circuit would look like. PSpice will also allow you kind of system level simulations, so you can create models in higher languages like C, C+, or System C, and use these models then in your circuit. You have also the possibility to make a co-simulation between PSpice, MATLAB, and Simulink. That might be interesting for you if you have to analyze some electromechanical systems where you have the electrical implementation in PSpice and the mechanical behavior in MATLAB Simulink. Now you can link these two simulations and run it at once. Or you have, for example, a very complex control regulation structure created in Simulink. You can make also then use of that. Okay, but today we will talk about the PSpice smoke analysis. So what is PSpice smoke analysis? PSpice smoke analysis is a so-called reliability analysis, because it will help you to find stressed components in the design. So stressed components, what are stressed components? Stressed by what? The stress can be caused by power dissipation. It can be caused by an increased junction temperature, for example. Components have voltage and current limits. Semiconductor devices have other kind of limitations like breakdown or secondary breakdown limits. And all these kind of limits are respected by smoke when the parameters are set. Why are stress components a problem for your circuit? Because the circuit may fail after some time when the devices are stressed. And stressed when they are not operated inside these so-called safe operating limits. The problem is when these devices fail and you have already shipped this kind of circuit to the customer, then you might have a really big problem because it is now very expensive for you to resolve that problem. First of all, you have to redesign. You have to exchange the circuits and so on and so forth. In the worst case, even your company's reputation may be damaged by such an action. And to avoid that, PSpice Smoke can really help you to identify these components which are not operated in the safe operating limits. So how do we come to these safe operating limits? Everything starts with the datasheet from the manufacturer. You know, these datasheets, they have already these sections like absolute maximum ratings or something else. And you put these values into the system, and these are called maximum operating conditions. The good thing is PSpice comes with a lot of devices, about 30,000 components, and for all these components, this is already done. So the maximum operating conditions are there. The next step is you apply a safety margin on the maximum operating conditions because you do not want to operate them at these limits. And that one is called derating. You have a static derating and there's a dynamic derating. Static derating is just applying a factor on all the parameters of the different devices. There are standards, and some companies have to apply these standards. Some companies have additional rules, company policies, so they have to add other deratings on top of that. And you might have also experienced designers who know, I will not use the device like the manufacturer tells me. I have a better choice to do that. That is static derating. Dynamic derating is also applied. That is, for example, a temperature or the power rating of a device, for example, for a resistor, is derated for the temperature. That simply means, for example, a 1 watt resistor can only operate within a temperature range with 1 watt power dissipation. If the temperature is too high, you cannot apply the full 1 watt power dissipation. The resistor would not be able to get rid of the additional temperature. And PSpice Smoke also applies this kind of dynamic derating then automatically. And so you come to these safe operating limits. And PSpice Smoke is then comparing the simulation results and checks if all the devices are operated within these limits. And then it says, okay. And if not, it will indicate that you have a problem there. So how is this done? How is this done in the design flow? This is a design flow. As I said at the beginning, the components must have these parameters. Then you start with your circuit development. For a circuit development, you have usually to fulfill some characteristics. You have specifications. You have implemented measurement functions, which will check if all the limits in the specification of your circuit will be okay. So that is your normal implementation and design work when you create a circuit. So you just check if the circuit is doing what you should do. And you're running here your simulations like transient simulations, frequency-based simulations, and so on. And you verify, yes, my circuit is doing exactly what I want this circuit to do. Normal process. And the one additional step then you have to do is just clicking one more button. And the one more button is run the smoke analysis. That's all. There's no additional work to be done here. Just click this smoke analysis button. I said at the beginning, you need to have smoke parameters defined. And I said also that all the components that are delivered along with the tool installation have already these smoke parameters defined. But now you have one more component for your circuit, which is not part of the standard models that are shipped with PSpice. How do I get to the smoke parameters? It's not very problematic because you have the PSpice model editor and you just have the data sheet from the manufacturer, and you can add to any device simply the smoke parameters. The table will show up with all the parameters that you can specify, and you can read these parameters from the data sheet, put them in. This is a one-time action, and once you save it, you have for this new component then also the smoke parameters defined. I will now show you here an example circuit. This is a so-called switch forward converter. This is a specific topology of a power supply, but this doesn't matter here. We are just focusing here on one specific device in this circuit, and this is this transistor here. This transistor is used in this circuit to switch currents on and off in a frequency determined here by a PWM generator. And this device, we will analyze, we will check if this device is stressed. When I run the smoke analysis after I have checked that my circuit is working, I see the results in smoke. And it's good that we have run the smoke analysis, because you see here's some values, here's some parameters that are marked red, and we have a problem with that. And we see that the maximum power dissipation is violated, it's red. And we see also that the maximum junction temperature for this device is heavily problematic, because we have here a calculated temperature of more than 1,200 degrees centigrade. Now you know why Cadence used the name smoke for this analysis. So that would not live very long, this device. We see clearly the problematic parameters for this device, and we have to act. What do we have to do? We have to lower, definitely, the junction temperature for this device. How can we do that? Let's just have a quick look at the formula, how the junction temperature is calculated. It's very easy, because the junction temperature depends just on the power dissipation and the thermal resistance for this device. The higher the power dissipation and the higher the thermal resistance is, the higher will be the temperature of this device. Of course, the simulation temperature is also depending or influencing here the junction temperature. So what can we do to lower this TJ? What we cannot change is this thermal resistance between the junction and the case, because that depends on the package. And we use just the fixed package. So what we can do, for example, is we can lower the thermal resistance of the case to the ambient, and that is simply called a heatsink. We can put a heatsink on this device and then lower this overall factor and see if we can reach here a junction temperature that we want to have. So here's just an example. I just say 130 degrees is okay for me, and I calculate from that formula the required RCA, just putting in the values from the simulation. That value comes from the data sheet, that's the RJC, and it calculates to 1.5 Kelvin per watts, what I would need for this heatsink. And then I put this virtual heatsink on my transistor in the design, It is just the parameter of the transistor. Just put it in the model edit in the parameters, and I run the smoke analysis again, and you see the result is below 130 degrees. Everything is green. I'm done. That's fine. Okay, that is one possible solution how to tackle this problem. I have here written down this formula again so that you can see RCA is not the only possibility you have to lower the simulation temperature here, the junction temperature. You can also try to lower the overall power dissipation. You can lower the power dissipation if you know a little bit more about these transistors, and the power dissipation is happening because the switching losses, and you have also the losses when the current flows through this transistor. That is mainly controlled by a resistance that is called RDS on. Just look in your database if you possibly find a part that has some better electrical characteristics for your circuit. And this is exactly what I have done. I have chosen simply another transistor. I've exchanged this transistor in the whole circuit. Of course, I need to check if, when I do something like that, if my circuit still works. So if all my other electrical characteristics are fine and the circuit works as expected. And when this is checked and I say, yes, I just have to replace here this transistor, then I can run the smoke analysis again. And I see, oh, still red, but for the temperature, I'm here now with 280 degrees instead of 1,200. So I'm coming closer. I'm also putting here a heat sink on it, and this heat sink is calculated then to 24 Kelvin per watts. I put it into the circuit, run smoke again, and see, hey, I'm below 130 degrees. It's fine. So this is another possibility to get the problem of your circuit resolved. And now I just want to compare or show you what I've done. That was my first device, a historic one. Okay, we need a large heatsink to cool this transistor down. I've exchanged it with a slightly better device, and you see I'm here with a very small heatsink that is then sufficient for this circuit. Here you see the difference in the RDS on. This device is 40 milliohms and this is 800. So this makes the big difference here for this circuit and for this choice. With that, I just will summarize what PSpice Smoke can do for you in a circuit. So PSpice Smoke will help to build really robust circuits which improve the long-term reliability. PSpice Smoke can be used whilst you're designing your circuit. So it's a really true analysis, early analysis, to identify the potential issues before you have started any production or manufacturing. PSpice Smoke can be used to run a what-if analysis, giving you the choice of finding an optimal solution where you, of course, decide what is optimal for you. You can buy, for example, a cheap component and you need a large heatsink, or you can choose possibly a more expensive component, but then you don't have the need for a heatsink or you need a smaller one. So with PSpice Smoke, or PSpice Smoke gives you really a sound foundation for making the right decisions regarding the component choices for your PCB. And now my colleague, Dirk Lindbrugger, will elaborate about further analysis possibilities within the Cadence design flow, analyzing the electrical and thermal effects on the devices placed on the PCB. And with that, I would like to hand over to Dirk now.
As Bernd just mentioned, we are now going further steps. That means we take into account, we stay here in this layout process. So what can we do in this stage, early stage, pre-design, post-layout, and so on. So in the past, it was very likely that electrical engineers had no idea about the thermal aspects. So they passed such problems more or less to the mechanical team, where mostly some thermal experts are located in. But on the other hand, the thermal department or mechanical department have no clue about the electrical issues and problems, and they only care for their work and their task. But nowadays, it's quite important that both teams, electrical and thermal and mechanical teams, work together to find a good solution for mostly their complex design. So in this case, we can use the so-called IR drop analysis to figure out issues that come across with current on PCBs that create voltage drops and also create high current consumption, high current densities on your PCBs. And of course, we also have to consider what happens if current creates heat inside these copper structures typically, and this changes the conductivity of copper, and then we have to consider these effects here in the electrical analysis as well. And in addition, we also have to take into account the thermal aspects of components. But step by step, we want to see, or I want to show you here right now, what can we do in which stage. So starting in the early design stage, we can use the so-called Security Aurora product, which enables you to keep in the PCB layout design flow without changing it to any other external simulation tools. In this Aurora, we have a couple of different signal integrity and power integrity analysis tools, but in this webinar, we only consider or look into the IR drop analysis. Just want to mention that in OrCAD Professional or OrCAD X Professional and Presto, the impedance and coupling scan are already implemented. You do not need any additional licenses for this, but all other require then this security license. So what is behind this IR drop analysis? What you do are these more or less a few steps. Starting here from your design, you typically create your layer stack up. It is essential, of course, for any analysis. In this case, you also have to define the plating thickness for vias, for example, because this also has an impact then to the simulation results. In the next step, you have to create, to define the so-called VRMs, voltage regulator modules. That means that is your source. And on the other side, you have to also configure your sinks. So in this case, we need as an input parameter the current that goes into the devices. Sometimes it's also necessary to configure some so-called discrete components that are located inside your power distribution network. That can be, for example, transistors, inductors, shunt resistor, or whatever else. They then are modeled with a very low resistance, and that gives you the chance here to model a complete closed current loop. Once this is all done, you can run the simulation and you get different options to visualize your results, either in tabular form or as we can here in this overview overlay. Once you're using or have to define more or less complex power distribution networks, you can do this with the so-called power tree. I will show you what is behind this power tree in the next slide. So, however, as mentioned before, we have to configure here some the sources and the sinks, and what you get is now the voltage drop. That means how much voltage will be created. Voltage drop will be created due to the copper resistance. You can also see the currents over your copper planes and the plane current density. So and the beauty of this Aurora is that you can do this analysis directly in this PCB editor and change change parts, positions, shape, edit vias and so on as you know it from the layout design process. So what is now here the power tree? It might be very quite complex. As mentioned before, you can create a very complex designs files or power distribution networks by loading your board file into this power tree, and that it extracts you all the things and sources. But sometimes it's even necessary or even to simplify your structure, because many of those components are not necessary in your power distribution network, and you can delete them. And what we also can do is here right now to assign the currents that in your things that are necessary for the simulation. Once this is done, you can save this file, and you can also use it for the security tools, for Power DC, for example, Celsius Thermal Solver or Optimize BI. So this is a very, very useful way to define your power distribution networks. Before I talk too much, I want to show you how this works in a short live demo. So what I did here is right now, if give me a second, I have to open it. So here it is. This is the typical user interface of Aurora. Here, when you say, okay, to analyze, you can open the so-called workflow manager. I've already did this here. And then you can choose the different workflows that are available. In this case, we want to use the airdrop, and starting with a simple VRM, simple structure. So just we have to set up the VRMs. We can select here the voltages. Maybe we use this VSUS 5 volts, and this is the voltage that we're checking for. And then we can say, okay, U2, I know this is my VRM. I assign it, and then my VRM is already assigned. And now we also need to set up the sink. Also can choose select here the correct voltage, and we also said, okay, we want to see the why is this by 5 volts, and here, okay, capacitors do not make sense, but we want to see here if we assign current to my D1 and also for a connector, let's say with a typical value of 1 ampere, but of course you can assign here any value that is realistic. So then it's already done, the setup is already done, and we start our analysis, and in behind the real security field solvers are running, and therefore it is not an assumption or a mathematical result what is coming out, but it's really done calculated by the field solver. So we are already done, and then we can see here, open here the current, the table formula. You can choose the pass fail. That means how much voltage is dropped due to your losses. But I think more or less it's interesting to see the visions. And then we select here to VCC5, for example. Then we can see how that would look like. And here in this case, 8 millivolts is not very critical, and because it is also a very simple structure. But let's see what will happen if we use a more or less complex power tree. I've already prepared that. That is the power tree that that has been that I've showed to you just before. So we have one voltage regulator and I think about 10 sources, 10 things. So everything is already assigned here, and the setup is already complete, and we can run our simulation right now. So it's also done. So already ready. Then we can see, okay, in this case, we have 125 millivolts of losses. That seems to be quite a lot. And what would happen here, once you're looking to such structures using your 4 eyes principle, for example, you may see, okay, here in this case, we have a maybe short track, and that might lead to a lot of losses. But once we enable here the current density, we would also see, oh, here, in this case here, we also have a very low distance that would create a lot of current in this case, and that should be avoided or even, yeah, should be replaced. And here we can see once we click on vectors, how that would look like. So let's maybe we can optimize this in a very simple way. So here we are now in the layout editor in principle, and we can say, okay, hey, maybe we enlarge this this shape here, this power shape. So you have seen here, it's now significantly wider, and maybe that I have to be a little bit more faster because of the time is running. We also have seen in a different way that we have here only one via that carries the current from the top to the bottom layers or to the inner layers. We may also add, we may also add some more vias in this case, and that maybe also help us to distribute the the current in an more efficient way. So here now I think I have it. So here you can see we do not need to change the layout tool. We really keep in the layout tool, so it's very easy to work with that. The database must be that is fully compatible to the ORCAD database or even Allegro. So once you are more or less familiar with using those layout tools, you may work with them, do your analysis optimizations here in Aurora, and then you can see, oh, yes, in this case, you can do your optimizations, and you see that the IR drop has significantly optimized from 127 to 100 millivolts. And maybe there are some more options to be done, but I think that is the way that we can go here. So I think that should be enough for this case, and let's follow on with my presentations and the next tools. So as a summary, now we can see here by doing some layout optimizations, you will really get good improvement, and that it's not only the improvement of the voltage losses, but it also improves, of course, in the later stage, the complete design performance. And taking into account here the via structures, that helps you to increase the reliability, of course, of your boards. Once you are doing this, only single via, that might get stretched very, very heavily over the time, and due to the changes or adding some more vias, that enables you to put away some more of those seeds. So in this case, he is now my next step, next item I want to talk about, because in this case, the IR drop analysis only uses, yes, the electrical aspect, but we also want to go ahead with those thermal aspects, and therefore we need to change over to the Security Power DC or Security Thermal Solver tools. And what's behind now about this the thermal co-simulation? So in principle, it goes like this, that you at first calculate the IR drop, and the IR drop, as we have seen, creates a current density at your copper phases. And this current will now be used as an input parameter for calculating the temperature. And once this is done, the temperature is calculated. It changes now maybe from the ambient temperature to a certain temperature now with the first run of those currents that has been used. This temperature will now be used as the next iteration step for an IR drop analysis. As I've already mentioned in my introduction, the copper and the PCB laminates are temperature dependent, and it means that the conductivity of copper changes. And now we go ahead with this new temperature of the copper, calculate a new current. This will be done here for the next step here in the thermal analysis, and so on until we get into a steady state stage. This really is not very complicated. You really don't make it understand or see it in your analysis. Maybe the IRO takes about 20 seconds and the complete ET co-simulation will be about 25 seconds. So that is very, very useful to go this way. In this example, we can see it's of course depending on the current that goes through your copper, that using only static analysis, but using also with the ET co-simulation that calculated IR drops, and of course the voltages, we can see here in this case, are significantly different, because here we also have to consider the temperature effects of components that are placed here on your PCB. That all can be done here with this ET co-simulation. I think that is very, very interesting to see now also for you how that works in a live demo. So in principle, we have to start again with the typical initial setup, as we have seen it for the R group analysis, create our power distribution networks with electrical analysis for sources and sinks. And the thermal setup is quite straight ahead, like similar to the electrical setup. So you need to set your ambient conditions. That means the temperature, and maybe also you can add some airflow into the design. But you also need to assign the components of interest that should be considered with the thermal as a thermal device, and then optionally you can also add some different heat sinks to your device to do for what if analysis, or to investigate if it makes sense to add those cooling concepts to your design or even not. Yeah, once this is all done, you run your simulation and get your simulation results, not only for the electrical but also for the thermal thermal aspect. What you can also do is to assign so-called transient behavior to some of your devices. That means, for example, here we can select somewhat like a piecewise linear function that mimics or that enables you to mimic the warm-up procedure of your components. And you also have some different thermal models that then can be assigned to some of your components. So in this case, maybe we use the two resistor compact thermal model, which is very familiar for to do this with for thermal analysis. It's quite simple structure, but it gives you a very good result. It gives you a very good results afterwards. The typical values here come from a data sheet in generally, and that's all that you need in this case. Now let's go ahead with such a design and how that would look like. In this case, I want to show you the setup for the transient design, but I don't want to run it in completely, because this takes about 150 time steps, and of course we are always running ahead with our time, and that I don't want to do. But I will show you how a simple ET co-simulation run would look like afterward. So go ahead, just a little. Let's have a good shot to our stack up. This is quite similar as you know it from the Allegro stack up, but here we also have pet stacks, and we can see how the diameters and plating thicknesses are assigned. But it's also interesting to see here with the material database that we have, I don't know how many different laminate parameters are given here, and you can of course add them, choose them, change them if necessary, and adapt them to your own devices. But it's not. But it's also necessary to see that we not only have the directly properties, but also we have thermal properties here in our design, and that makes it interesting to see how this will behave in our simulation. So then we are done through. This is done here. I've used here the same PDN structure as I've already divided here with the power tree. Here in this list, we now can see that we not only have one VRM assigned, but also more. So that might be interesting to see, or to see what will happen on your ground planes, because when you are running with many PDNs in parallel, this may also have an impact to the current on your ground planes. Here, of course, the things are also assigned. You see, we have many more here in this case that can run in parallel. The thermal components now are selected here from the component manager, and once this is done here, you see some of them are already located, and then you assign the power dissipation to the devices. Model, maybe change some models, as we have already seen just in my presentation, and you also can edit here the PVL or the transient function to all of your devices. So once this is done, yeah, we can also maybe add here this heatsink, as we also have seen in the slide before, and you can see that we have several different types that we can use here to configure your different cooling concepts, if this is necessary or even wanted from your side. So I think that is more or less done. I will skip now to set up the electrical and thermal constraints, because this enables you directly here to define maybe for the electrical design current maxima, voltage drops maximum, and so on. And then in the result table, you can directly identify if there are some problems in your design, and you can directly jump to it. So this is a result already, but I want to rerun the simulation so that you can see how long that will take. So it's exactly the same setup as I've just showed to you, but now only with one ET co-simulation run, and even not this 150 steps that I've used for this transient analysis. And you can see that we are, well, yes, the system is running. Now here we are going through the different layers. It is meshing. The meshing is now displayed here. Now the results are calculated from the results table. And in this case, the simulation is already complete. Now it enables you to brings up the simulation results to your devices, and we can see. Yeah, that's what I want to see you now. What we can see here for the temperatures, and you can toggle through all the different layers. Maybe also have to look to the heat flux or conductivity. We can also directly identify hotspots. Yes, you can see here, then it is shown here. And you of course have many options here for visualization. And I think that is very interesting to go through to improve your design in a very, very early stage, or even when there is when you have already routed some layers. It's also possible to create a report. I think I've done it here. The report, might be also very necessary or interesting to have it on hand for to see what's happened here in behind. And you can see that for this transient analysis, each layer for each time step was printed out with voltages, temperatures, and so on. And that may also give you a good indication if this is if you did your work correctly, or if there's still some possibilities for optimization. So due to the time, I have to switch back now to my presentation, because I want to summarize here the results. So in this case here, the ET co-simulation, as mentioned, is based here on the RDROP analysis, but it also includes here the thermal aspect. And as expected here, where we have this very narrow shape, the temperature is of course higher than in the case of where we have expanded the shape. And we also can see here, by adding some more vias in the we can lower the current in through the vias, and or even if you make the traces wider, we can not even reduce the current, the IR drop, but we also reduce the temperature significantly. I think that is a very impressive result here. So, as mentioned before, we also can make some what-if analysis by taking into account the effects of some active cooling, active or more or less active, by adding some heat sinks. And finally, we can see how the transient analysis works, starting here from the beginning, when we are starting here from ambient temperature to the final results. And that can be also seen here in this ramp up temperature curves, where all those where the temperatures are located at different time steps. We have some interesting white papers or onto this measurement that compares measurements with these simulation results, and upon request we can share them with you, because it's very interesting to see that we are very good correlation between simulation results and measurements. So with this, I want to come, or I have to come to an end of my short overview to Security Aurora, the InDesign analysis, and the security tools, Security Thermal Solver for electrical thermal co-simulation. And I hope that will help you to identify some issues in your design, and maybe also opens you some ideas for new ideas of how to place maybe some components. And it enables you, especially, that is very interesting to see, that you can do some simulations without the need of any prototypes, and nothing can break, because the simulation gives you a result, and that helps you to deliver your product to the right time at birth. So in this case, I want to stop with my overview, and I want to invite you to a workshop where we want to show you how to work with these tools. That means the Security Aurora and also with the security tools. So I would really be happy to see you in this workshop, and that helps you, maybe also helps you to get into contact with the tools, to learn how that works, and hopefully that enables you afterwards your work for in your own company. So thank you for your attention so far, and I want to give back to Petra.
Thank you very much.
Okay.
If you have questions, like to have a special demo for yourself where you can get into special topics or so, please give us a call, send us a message. Thank you very much for your attending today. Have a great day and see you next time.